Hello, and welcome to another lecture presented by www.free-academy.com. In this lecture, we're going to cover the derivative rules, and this is going to be two basic things. When you can apply the derivative, and a couple of things on how to apply the derivative. This will be techniques. What we're going to do now is we're going to get away from using the rigorous definition of the derivative and start using more efficient methods such as the power rule, product rule, chain rule, and so on and so forth. But this is our prerequisite here. So when you apply the derivative, you can't always apply it. See, we did it on a parabola in the derivatives lecture, and that's fine because everywhere you look on this you can have a tangent line all the way up to infinity. It always works, but that's not always the case. For example, hold on. Sorry, my computer seems to be a bit slow. If you have a function that has a corner in it, for example, like the absolute value function, this would be along the lines of negative x minus 2 plus 3. That's about what this is right there. I just kind of made it up. Oh, don't need that. That's about what this is. At this corner right here, what's the derivative? I mean, is that a tangent line? Is that a tangent line? Is that a tangent line? They're all tangent lines. If you go anywhere else on this derivative, you always know what the slope on it would be, but at the top you don't. I'm using yellow. It won't work. No idea. So there is no derivatives at corners. And I'm going to use the derivative notation at corners. And there's another time where you can't find the derivative. If you have a vertical line somewhere inside the function, there is no derivative at this point here. And there's another reason why, because you have two potential tangent lines. This could either be negative infinity or positive infinity as the slope there. So, no vertical lines. Another case, if you have just points, there are no derivatives at points. Again, anytime you get into a situation where you can have multiple tangent lines, you cannot have a derivative. So those are the three big ones, but the rule is in order to find the derivative at f of x, two conditions must apply. F of x must exist at that point, the derivative at c. Sorry about that. The derivative at, tripping over my tongue here. In order to apply the derivative of f of c must exist at, f of x must exist at c, and it also must be continuous. So I know I stumbled a little bit there, but f of x must exist at c and it must be continuous at c. Alright, so that's when you can apply the derivative. I'm going to erase a little bit, and we're going to get into a couple of things about how to apply the derivative. Guess I should have just gotten a new sheet of paper. Alright, that's good enough. So, let's say you want to take the derivative of f of x plus g of x. How do you do that? Well, let's, to do it by example, let's say f of x equals x squared. and g of x equals 2x. So you want to find the derivative of x squared plus 2x. So what we have here is the addition rule. The derivative of f of x plus or minus g of x is going to equal the derivative of f of x plus or minus the derivative of g of x, respectively, of course. If you're adding g of x, then it's the derivative of f of x plus g of x. If you're subtracting, then it's f of x minus g of x, of course. So we would take this as the derivative of x squared plus the derivative of 2x. Now you can check these using the rigorous definition, but that's going to come out to 2x plus 1. And when you put this into the formula, you can either do this separately and add them together, or you can actually put in 2 of x plus x, and that'll be more difficult, but you can do it. So that's the additive rule, as it's typically called. Now we're going to do the constant rule. This is not like an actual name here, but this is just how I go about it, what I call it. So if you are going to find the derivative of c times f of x, where c is a constant, it can be 4, it can be 3.2, whatever, just as long as it's constant, that's going to, you can actually pull the constant out, then find the derivative. And we actually kind of did this before. We did the derivative of 2x before. What we did is we pulled the 2 out, then we found the derivative of x, and then we multiplied the 2 back in. So that's a pretty easy one. The other thing is the derivative of any constant always equals 0. It always equals 0. It does not matter how big the constant may be. It is always going to equal 0. And let's look at why this is graphically. So let's plot f of x equals 2. 1, 2. Well, what's the slope on that? That doesn't have any rise over its run. That's 0. And if we're going to find f of x equals negative 4. 1, 2, 3, 4. Again, it has no slope, so the derivative of a constant will always be a 0. Now, to review this lecture really quickly, in order to apply the derivative at f of x equals c, f of c must exist and be continuous. And f of x plus g of x, the derivative of which equals the sum of the individual derivatives. Constants can get pulled out in front. One taking the derivative. And the derivative of any constant equals 0. So those are going to be the basic rules that you need to know in order to do more complicated derivatives. This is all very easy stuff. Next lecture is the power rule.